All right, welcome everyone. Today we're going to be diving into our very first Code Platoon iteration of learning models. We're going to be talking about learning models, how to utilize a framework named PyTorch. We're going to cover virtual environments and what they actually do and how they work within our machines. And we're going to talk a little bit about the entire neural network process. How does training happen? How does the algorithm, how does the AI or learning model actually learn to provide good answers? Then we're going to covering the install fast for PyTorch. We'll then talk about tensors, which are just going to be something that we're going to become extremely familiar with for the remaining of this module. The next 7 days, we're going to be working with nothing but multi-dimensional arrays, and we'll see how it all compiles into one massive OP learning model, which is going to be built in a class-based. It's going to work with a text, the language that we provide to it in order to be able to provide responses for us. And we'll be able to ask it questions and get accurate tokenized responses from it. At least that's our goal. All right. Does anyone have any questions over what we'll be covering today? Erica.
Will we be seeing a little bit of TensorFlow too?
Will you be seeing what? TensorFlow?
Yeah, a little bit of it.
We will not. No, I believe the stuff that we're going to be looking at mainly will be PyTorch. We'll be looking at a little bit of Pandas and a bit of NumPy as well while we're working throughout this module. All right. If there aren't any questions, then let's go ahead and get started. The very first thing that we're going to talk about is what exactly are learning models? What do they look like and how do they work? Well, learning models in layman's terms, I'm sure everybody has heard the saying of if you throw enough if you throw enough things at the wall, something eventually will stick, right? Well, that's kind of how learning models work. You just consistently throw a ridiculous amount of data at the wall and you tell it, hey, this is the stuff that you're supposed to retain. And you continue doing that process over and over again until the learning model actually understands, oh, I have to retain this information. The rest of it can get dumped, right? So a learning model looks something like this. I'm actually going to move this virtual environment stuff so that we could talk about it later. So a learning model looks something like this. This is something called a fully connected neural network. And we'll break that down later on. We're not going to go over different types of neural networks. We'll stay within a fully connected throughout this module. Essentially, what happens is we provide an input. From that input, our data gets broken down into smaller tensors or smaller neurons per se. And inside of each one of these neurons, there's some sort of mathematical operation that happens, and these are called weights and biases. The weights are represented by the actual dumbbell, and the biases are represented by that hourglass, right? So weights and biases are happening, and essentially the next layer gets built depending on the mathematical operations that happen on the layer before. And it continues doing that and tries to provide an output that's similar to the answer that we want. Right, so a clean example of this, which we'll be talking about tomorrow, will be in reference to potable water. And let me go ahead and fix this because for some reason this thing ended up all mixed up. Oh, wow, it is bad to go. All right. Let me give it a second attempt here. There you go. So potable water will come in. Well, how do we determine if something is actually drinkable? Something can be consumed for us in a healthy way. Well, there's actually a whole system that determines like a certain pH level, where the water originates from. If the water is like a certain level of stagnant, I'm nowhere near as intelligent as I should be as to what actually determines water to be drinkable. I kind of just open up the faucet and drink it. So there you go. But there is some statistical data that tells us whether water is actually drinkable or not. And usually that statistical data is interpreted by ones and zeros, where zeros say, hey, this is false, and ones say, hey, this is true. Sometimes we may see something that's being interpreted as floating decimals, but that's not necessarily always the case. Well, this data here of this ones and zeros gets fed into our input. And essentially what we want to know is, hey, is my water drinkable, right? Can I drink this? Well, what we're going to train our learning model to do is to take this initial batch of data, I wanted to take this initial batch of data, pass it into the input, and then from there, it's going to simply replicate this information to the first three tensors, right? Or the first three neurons. We'll grab the same amount of information. And from there, the information will mutate. It will change some of these ones and zeros. They may turn into floating numbers. They may not turn into floating numbers. Most of the time, we'll be dealing with floating numbers here because we want a high level of precision. So we'll be dealing with floating numbers that go all the way to the 32, or yes, it is 32 integers of precision past the float. And then it'll continue to mutate from one level to the next, to the next. And then finally, even though my input data was ones and zeros, my output data will either be a 0 or a 1, right? It's going to get this massive amount of statistics, mutate and continue mutating, and then spit out a 0 or a 1. 0 meaning, no, this is not drinkable water, and 1 stating, yeah, this is drinkable water, right? Now, it's not going to get this on the very first try. It's the very first time that we feed this information through it, it's going to be completely wrong. It's going to be all over the place, right? But what we're going to do is we're going to run something called a training cycle. So every time this information gets fed into the model, at the end of it, we're going to run an evaluation, right? We'll have our separate data set that will say that for this specific data, this is all supposed to spit out true, right? It's supposed to spit out 1 for us. Well, every time it spits out 0 and it's false, we're going to run a back propagation step, right? Where essentially we're going to tell the model, hey, this is wrong. Adjusts the weights and biases at each one of these neurons so that the next time this data gets fed through the loop, you spit out 1 instead of 0. Right? And that's all that's happening. We're just continuously feeding it data, evaluating if that data is correct. If that data is correct, we're telling it, hey, these are good weights and biases, attempt to sustain them. And every time the data is wrong, we tell it, hey, this data is wrong. You need to adjust these mathematical operations that you're running at each neuron so that the next time this data gets fed, you can give me the correct answer. Right? And that's all essentially learning models do. They're just running math under the hood. Even when you're trying to talk to something like ChatGPT, every single one of your characters or your text is not actually understanding language. It's just turning each one of those letters into a numerical value and interpreting that numerical value at each neuron, trying to find you an answer that would match what you're asking, that would match this series of characters. Does that make sense to everyone? Does anyone have any questions regarding learning models or how they work? All right, let's hear it, Brendan.
So they are just extremely complex if-else statements.
Essentially, right? We're not really going to be writing these if-else statements off the bat ourselves. Luckily, that's what the framework is going to do for us, right? But yes, every time it gives me an answer, I'm saying if this is true or if this is correct, sustain all of your math that you're doing If this is false, I need you to change it so that it gives me a correct answer. Is that kind of what you're asking there, Ben?
I think so. And so the framework just allows us to manipulate multi-dimensional if-else statements.
Yes,
what we're
without us
building.
having to, yeah,
Okay.
without us having to do it manually. Erica?
So, in yeah, I would say based on it's also instead of it necessarily being a 0 or a 1, it is between a 0 and a 1, trying to reach as much of the 1 as you can, and that's what like modifies the weighted biases.
Yeah, definitely. That's correct. When it spits out the answer, it's not necessarily going to be exactly a 0 or a 1. And we'll go further into how we'll do these binary evaluations tomorrow before we go into multi-classification. All right. Well, that's our neural network. That's kind of how it works. It's actually, I mean, I think it's really cool because when I was first learning this stuff, and I was learning about each individual neuron, the very first thought that went up to my head is like, you're telling me that I have to go back and update each individual neuron one step at a time every time it feeds me wrong data. And then later on, when I learned about the backpropagation loop, it amazed me how easily you could just send information back through the loop without you having to do it manually and tell it, hey, this is wrong. You need to fix it by this specific number of steps, right? So that's our fully connected neural network. The next thing we're going to be talking about is going to be our virtual environments. How do virtual environments work? What do they do? And where do they live inside of our actual machine? Now, we've talked about virtual environments before, and for all of us who did install Fest correctly, currently you should have a .default being activated in the lower left-hand side of your terminal, whether you're running ZSH or Bash. All right. We've been using this Python virtual environment, but why? What does it do? We haven't really talked about its purpose. Well, the good thing about learning about node projects and working on all of the different Beat projects that we did is that we've learned a lot about dependencies that fall within our projects, right? Some of them utilize something called React Router. Some of them utilize something called Axios. Some of us might have chose not to utilize Axios the entire time we were learning Vite and React. Some of us might have just chose to run with fetch and never utilize Axios, right? Well, as we continue to run npm install, we saw that our package lock JSON was being expanded, right? Every time I installed something, my package JSON was expanding as far as dependencies. My package lock JSON was expanding as far as version control, keeping track of what version I was utilizing from each individual dependency. And then my node modules was just, even though I never looked at it and I never touched it, if you ever go back to one of those projects and open it up, you'll see that as you install things, the node modules directory just continues to grow and grow and grow. Well, what's actually happening there is every time you run npm install, you're not just doing a magical process, right? As we've learned so far in computers, everything is just directories and files over and over again. Whether I download something from the internet, whether I download maybe like a Game Boy emulator into my laptop to be able to play Fire Red, all that is a directory that when I open it up and I choose which file it is that I want to run, it's compiling some sort of code and opening up a user interface that's built in some sort of front-end framework so that I can interact with it and play the game, right? We've got that so far. Well, what do virtual environments actually do? In most machines, you already have a version of Python installed. I'm not gonna say that Windows machines come with Python installed. I'm pretty sure they do. So far, I know that Mac definitely does come with Python already pre-installed within it. But I don't necessarily want to utilize the version that's installed inside of my machine to handle all of my dependencies. Now, the question may be, well, why not, right? It's already inside of my local machine. Why wouldn't I utilize it? Well, in my node modules, or whenever I went ahead and created a node project, if I delete the directory for the node project, all of those different node modules that were being installed are now gone. They're no longer occupying any more of my driver space, right? They're not occupying memory space inside of my actual local machine. Well, that's kind of what virtual environments do. They give us a clone or a different form of a Python that still has all of the functionality that Python does. I can still run pip. I can still run Python scripts. But when I delete that folder for my virtual environment, all of the different dependencies that were installed within that virtual environment also leave my disk space, right? So there's one benefit. It's something that I can easily remove so that it doesn't continuously occupy disk space. So it allows my computer to stay efficient, right? Now, what else do virtual environments do? Let's say I'm working in 3 separate projects, right? I'm working for some sort of consulting company. I have 3 separate projects that were handed down to me, and they were all built at different times. Maybe one of them was built back in 2000s. One of them was built maybe like around 2010. And then the last one that I got was the more modern stuff that we've seen lately of 2020, right? Well, the one that was built back in the 2000s is utilizing Python version 2.1, right? And that's definitely not what I have in my local machine. And I don't want to revert the Python version in my local machine all the way back to 2.1. So instead, I could start a virtual environment, revert my Python version back to 2.1 so that I could still run that project. I could grab the specific version of Flask so I could run that project. And I could grab the specific version of pip so I could execute that project. Additionally, I could start 2 other virtual environments that have the correct dependencies, which is the Python version, the framework that I'm utilizing, and the pip version. All right, over here, we can see that this one even utilizes something called Django REST Framework and Psycho PG3. So I'm able to have all 3 of these virtual environments to run all 3 of those separate projects without ruining one another, right? The dependencies are being isolated for each individual project. Just how when I create a project, each project has its own node modules directory, its own package lock JSON, and its own package JSON inside of Node. Does anyone have any questions regarding the purpose or the benefits of Python virtual environments? Let's hear it, Tim.
Yeah, so I understand that each project has their own objectives, etc. Is there any reason why you would use Python 2.1, 2.15, and then Python 3, or just to see if it works on older Python, or would you just always use Python 3 most of the time?
Yeah, that's a great question. There are going to be times where you're going to be working with projects that are super old. Some projects that are older may utilize a different version of Python. Maybe the newest version of Python that we're currently working with hadn't been released. And although you may think, well, the differences are probably very minute and I can still compile the code in Python, that's not the case. For those of you that did the Intro to Coding Live course that we have online, you'll see that before in JS, you run like print statements and console.log statements without the parentheses being included, right? Well, that's no longer the case. Now you need those parentheses to be able to actually conduct a print statement and call the function, whereas in a previous version of Python, that wasn't the case. Does that answer your question, Tim?
Yeah, thank you so much.
Of course. All right. So now that we've talked a little bit about virtual environments, we're going to create a new one that we're going to utilize strictly for handling our learning models. Now, I'm going to go ahead and create this. I'm going to go on a little bit of a tangent here about handling your virtual environments. I've seen it a lot where people create virtual environments on the same directory as their project. You definitely can. Just letting you know, right? One of the biggest reasons why you should utilize virtual environments is to save up disk space, right? To make sure that what you have is something that's correct, or something that you actually need. If you continuously just put these virtual environments in various different locations, what's going to happen is they're going to end up living in your machine forever, and you're going to completely forget about them. And then you're just going to have all different kinds of virtual environments living inside of your local machine. So for organizational purposes, what I do is inside of my root directory. So if I change directory to root, I have a directory named environments. I created this directory myself, and this is where I manage all of my environments. All right, from there, I'm going to go ahead and run Python -m VNV. So I'm utilizing Python to execute the command virtual environment. And then I could name it whatever it is that I would like to name my virtual environment. In this case, you can call it learning models env. So that the next time I go into this directory, I can easily identify which virtual environment it is that I'm trying to utilize for this project. All right, I see a question from Len. Go ahead.
So I'm tracking where you're at. When it comes to going back to using JavaScript and having the directory there, and then you like dependencies get stripped out when you push it to GitHub. Is this a similar idea? And are we going to go over like how that gets implemented so when we push it, it doesn't get the whole thing to GitHub?
Yeah, we're going to be learning about what you're talking about, something called a git ignore file, which essentially tells Git to ignore specific files or directories. We won't be covering that today. That will be covered on later on in the course. Does that answer your question, Lynn?
Yeah, it does. And this is the same as the locked file-ish.
Right. It's managing our dependencies, kind of the way that the lock file did. Right.
Thank you.
All right. So now I have my Python -m vmv .lm env. Well, when I execute this command, it's going to take a while. There it is, created my virtual environment. And if I run ls, we'll see that I don't have anything. Why is that? Why is it that I can't see all of the directories that are living inside of environments? Let's hear it, Brandon.
Decided to add a dot in front of it so it's hidden, so you have to do ls-a.
Nice. Yeah, I have a dot in front of it. So I have to run ls-a so that I can see all of my dot files, right? So there we can see that I have my lm env being created inside of environments. Well, now how do I activate it, right? Well, in order to activate this environment, I could activate it from pretty much anywhere in my directory. I just have to map into it, right? Now, what do I mean by that? Let me go ahead and open this up in a separate VScode terminal here. All right, so currently, all I'm looking at inside of my file directories are going to be my learning model environment. All right, and I'm mainly concentrating in this learning model environment. Now, keep in mind, this are just scripts, right? These are all just directories and scripts inside of it. Well, how does this work? Let's start from the bottom. This Python virtual environment.config, what is this doing? Well, what this is doing for us is actually configuring so that every single time I execute a command within my shell, instead of executing that command at my actual local machine's Python, it's giving it a path. It's saying, hey, you don't want to do this in the local machine's Python. Instead, you want to execute this command within the learning model for the virtual environment, right? Same thing for executable. We'll see that it routes all the way to the learning model's virtual environment. This includes system site packages. I have no idea what it does, if I'm being 100% honest. And then it has the root home directory for my actual Python so that it can protect it later on when it references the virtual environment, all right? So there's my config file. it just interacts with the shell directly. We won't necessarily touch this file. It just tells the shell, hey, when you execute a command, this is where we're going to execute the command. It's going to be from the from the virtual environment itself. All right, let's take a look at include. Include just has a directory named Python 3.12, but nothing inside of it. Okay. What about lib? Well, lib has a little bit more stuff, right? Lib has Python 3.12, then it has a directory called site packages, and then we have pip and pip24 with a couple of txt files. Well, remember how I mentioned how our node modules grows every time you make an install? Well, in a virtual environment, your lib directory is going to grow every time you install something from Python, right? All of those executable commands, such as something like React Router, was getting the code that actually built React Router was being referenced to or stored within node modules. Well, in this case, it's being referenced to or stored within lib, right? And then here's the important stuff. The bin functionality or the bin directory. Well, you realize that in the bin directory, we have something like Python, Python 3, Python 3.12, and we have pip available as well. Well, what are these? Right? If I click on them, it's going to tell me, hey, this is an unsupported file. And if I say, yeah, I want you to open it anyway, I get all of these nulls and different weird characters. Does anyone know what we're looking at here? All right.
The binary.
Yeah, we're actually looking at some binary code here, right? These are all our ones or infamous ones and zeros that we're supposed to somewhat at least know that they exist there, right? Well, Python is actually built on top of C, right? And when C is compiled by some sort of compiler, it spits out some binary code or a binary file that looks like this. And this is the executable code that is actually being executed by our local machine. So Python, or the version of Python that we have here for all of them, they're just the different binary compiled codes for each one of them, right? So when I execute Python whatever script or Python whatever script, this entire script of ones and zeros gets executed. It then grabs the script and it utilizes it to create, read our code, and execute our Python scripts, right? Well, now, what about this activate function? Well, if I take a look at this activate function, if I see that money sign, it means that it's a shell script. It means it's interacting directly with my shell. And we'll see that this one specifically carries the deactivate function, right? So this is how I turn off my virtual environment. Here's a bunch of aliases, a couple of set environment paths, other things that interact directly with my terminal. And I'm actually looking for the function for activate. Oh, excuse me. There's no actual function for activate. When I run the activate command, or as we think it's the activate command, I'm actually just executing this script here. And this entire script is just interacting with my shell, building a bunch of references to the path, and telling my shell, hey, I want you to utilize this information to execute Python code moving forward, right? And for those of you who like to work in Windows and still utilize PowerShell, there is an activate script now for PowerShell as well. All right. And that is all we are creating when we create a Python virtual environment. Does anyone have any questions regarding the folder structure and what we're actually creating when I run Python VMV virtual environment? Let's hear it, Gary.
Yeah, did you say you created the environment folder?
Yes, I did. I created a directory named lm env, and that created these directories down here along with that file.
Okay, gotcha.
Let's hear it. Oh, any other questions? All right, let's hear it from Cody.
Yeah, is there a way to find out if you have virtual environments open other than knowing where they're saved at?
I'm sure that you can write some sort of script that will look for some naming convention. Hopefully you had a naming convention for it. Other than that, maybe you could look for a specific directory pattern. I'm not sure of a command off the top of my head, but I'm sure you can write a shell script that will do that for you. Of
Thank you.
course. All right. Doesn't seem like there are any other questions. So let's go ahead and take a step back and go back to our project now. Well, just like I saw, the file that I want to execute is within this .lm directory, right? I can go into .lm for env. I can go into the directory named bin, and in here is my activate script, which is what I want to run. Again, this is just a directory in scripts, so I can run this script from any place inside of from any location inside of my computer, as long as I can find the correct path, all right? Well, I'm going to go back to my actual curriculum here. If I do pwd to print my working directory, we can see that I'm inside of X-ray demos and notes, and I'm inside of a series of nested directories there, right? Well, how do I activate my environment now? The command that we utilize to activate our environments will be source. I am telling the shell, hey, for any follow-on executions, I want you to utilize this file as a source. And the file that I want to utilize as a source is the one stored in my virtual environments. So I'm going to utilize tilde to go back to my root directory. Say I want to go inside of environments in .lmenv/bin/activate. Right? I am just specifying the path to my activate script so that I can execute it. And now when I execute it, we'll see that I have this .lmenv for learning model env. It has now been activated, and anything that I do within this virtual environment will get stored in here. All right. Does anyone have any questions over how to activate your virtual environment? Okay, well, now that I've activated my virtual environment, I can go ahead and upgrade my pip version, because currently my pip version, for whatever reason, whenever you create a virtual environment, doesn't come with the newest one. So I'm going to run pip install --upgrade pip. And I'm going to share this command here in the X-ray questions as well, so that everyone has it. All right. Now, when I run this, we can see that some things were being installed. Some of them were already satisfied, right? So pip was already satisfied. But the newest version as pip was then collected and successfully installed. Okay, great. I have the newest version of pip. I see that my virtual environment is working correctly. Well, how do I turn it off now? Well, the way that I can turn off my virtual environment script is running inside of my terminal, deactivate. And now you'll see that on the lower left-hand corner, the learning model env is now gone. Does anyone have any questions regarding how to turn on and turn off your virtual environment? Let's hear it, Eric.
Do you have to be in a particular directory to run deactivate, or could it just be like anywhere?
Yeah, that's a great question. Let me go ahead and bring up that code one more time here. And let me go here. I can actually just put code in here. Well, if we look at the activate function or the activate script that I ran, there's this deactivate method that's being installed. And that actually sets it as an environment variable into the shell, right? And we could see that here, where it says, hey, there's a deactivate structure that's being set into the shell. So anywhere within my shell, as long as this virtual environment is activated, if I type in the keyword deactivate inside of my terminal, it will route back to that virtual environment and deactivate it. Does that answer your question, Eric?
Yep, thank you.
Of course. Tim?
So when you're deactivate, or why would you not use default as your primary virtual Python environment? Why would you name it something else?
Just almost like anything in coding, you want to be as specific as possible, right? Imagine that you have like in this example, if you had a series of projects, right? And then you just name it default 1, default 2, default 3. Well, a couple of months go by, maybe you go on vacation, you come back. How do you know which default directory or which default environment belongs to which project? Right?
Yep, that all makes sense.
Okay.
Thank you.
Of course. Len?
I'm going back to the lock again because it just makes sense in my brain with what Tim just asked. Like every time you make an environment, it's for a project, and you kind of think about like the lock. So it's like for that project or any, I mean, maybe a group of projects, but it's like, it's the idea is that dependencies for a set of things you're working on. Therefore, if you have 3 different people, as you mentioned earlier, you'd have 3 environments, maybe 1 for each group.
Yeah, that's correct.
You don't have to do it that way. You can just create one. Like you said at the beginning, I can just do my root directory and do it there, and you kind of screw yourself. So you use the environments to like parse everything.
Right, exactly.
Cool.
All right. So now we've covered a little bit about creating this virtual environment, how it works. Well, now we could actually go into the good stuff, right? I've done all of this, and I've done it with the purpose of actually being able to install PyTorch. Well, what is PyTorch? Let's take a look at PyTorch real quick. So PyTorch, here is their main site. This is how to get started locally. If you look up PyTorch, it's going to come up with a link called Get Started. I just shared the link to it as well in the X-Ray Questions channel. Now, what PyTorch actually does is it allows us to work with multidimensional arrays. And it has a couple of features from other data-oriented frameworks such as NumPy and Pandas already integrated within it. We'll go further into that once we actually start diving into our learning models and building all of these tensors. But the important thing to realize here is, or the main thing that I want us to get out of this, how simple it is that they make it to install this information. It tells you that there's a couple of ways of doing this. You can install it through Anaconda, or you can install it through pip. Anaconda is more of a, I click buttons and things get installed. It's mainly used for more of like data-driven information, studies that happen within college or anything, other research paperwork, whereas pip is more for us, right? The developer standard here. So I want to utilize pip. It gives me a little bit of guidance as to how to run this information, and it tells me how to do some verification as well. Well, the easiest way to do it, at the very top, it gives me a very easy click button so that I can tell it what operating system I'm in. This lecture is mainly designed already to follow with Mac. But I've experimented with this information as well. And whatever we are able to compile on Mac, you will be able to compile inside of your WSL machines. So please don't stress out about it. Everything's going to work as intended, right? So we could utilize the preview, which essentially it's telling me, hey, this gets updated on a nightly basis. Like we're consistently working on this, and every night there may be a new version, may or may not be a new version. I don't necessarily want that. I'd rather just utilize the stable version, make sure that what I'm using has been tested, works, and other people in the community have used it before. Oh, excuse me. I'm so sorry, guys. I apologize about that. So here we are within PyTorch, right? I want to utilize a stable version. And this stable version is going to ask me, well, what operating system are you on? I'm currently on a Mac operating system. It tells me what version, what are you utilizing to be able to install this information? I am installing through pip. And then it tells me what language you're using, C++, Java, or Python. Well, I'm utilizing Python. So it already scratches out which kind of compute platform I'm able to utilize. The only compute platform that I'm able to utilize is the default platform. And here's the command that I'm able to execute, right? pip3 install torch version. Excuse me. All right, so here's the command that I'm going to be utilizing to install PyTorch. So let's do it, right? Let's actually install PyTorch into my virtual environment. I'm not necessarily installing it directly into my local machine. It will be executed by my local machine, but it's going to live inside of my virtual environment. I'm going to utilize the source command again, go into environments.lm environment bin activate. There you go. I've activated my virtual environment. We can see that is an LM env. All right. Well, now I'm just going to run that install command. All right. It provided it for me, so I could go ahead and use it. I'm going to run pip install torch vision torch audio. And we can see it going through the process of installing everything that I need to be able to utilize PyTorch. All right. There you go. It's done. It has officially been installed. I now have the PyTorch framework inside of my machine. Just to do a real quick recap over how I did that, I went over to the Get Started site for PyTorch. I selected stable because I only want the stable version. I selected my operating system, which in this case is a Mac. If you're on WSL, you're not necessarily going to use Windows. You're instead going to use Linux, right? Then for my package, I'm utilizing pip. The language will be Python. My compute platform, because I'm on a Mac, it's already telling me default. If you're on Linux, please utilize CPU. And then finally, I run my command that is given to me inside of my machine to be able to install PyTorch. All right. At this point, does anyone have any questions regarding the installment of PyTorch? All right, a couple of questions. Let's hear it, Mikhail.
And you have to be inside your virtual environment before you can run that command, correct?
You don't have to be. If you run it from within your local machine, it's going to work, but it's going to be installed into your local machine and permanently utilize that disk space. Whereas if you install it into your virtual environment, you could remove it later.
Okay.
So you do it within your virtual environment.
All right.
Chris?
Do you already have instructions, I'm assuming, in GitHub for us to do this later?
Yes, everything's already on GitHub as far as install fest.
Gotcha. Thank you.
Tim?
When you make a virtual, it's utilizing the RAM instead of your actual memory. Is that, and then when you restart your machine, it's gone? Or is that how it not works?
That's a great question. No, it's still going into your C drive. It's still occupying memory space. The difference is that when I delete that virtual environment, all the memory space gets freed up, right? And I strongly recommend that you don't ever delete the pre-built version of Python that's already installed inside of your local machine. right? That's not
Sure.
necessarily what we want. So we want to
Yeah.
isolate this behavior.
So the Python virtual is in the C, but it's gone when you restart, or is it gone when you tell it to be gone?
It's gone when you tell it to be gone.
Okay.
Eric?
So are we gonna have to deactivate our default virtual environments for this assignment to create a new one, or how's that gonna work?
Yeah, definitely don't have multiple virtual environments activated, right? It could create some misbehavior. So when you type in deactivate, it will deactivate any number of virtual environments that you currently have. And then from there, only activate the one that you're utilizing for learning models. Does that answer
Okay.
your question, Eric?
Yep, thanks.
Of course. All right. Okay. Doesn't seem like there are any other questions. I have PyTorch installed. Well, how can I verify this? Well, we're moving forward with our Linux. We're moving forward with our Python. So it's time that we start seeing a little bit more advanced Linux commands when it comes to Python, right? Well, Python, we've seen the Python playground, and I can do a couple of things here from the Python playground, right? But there's an easier way to execute information in Python. I can say Python-C. This is going to take into quotation marks my Python code. I'm going to import torch. And from there, I'm going to print torch dot underscore underscore version underscore underscore. Now this import torch, I am importing the PyTorch framework. And if we go down to the verification portion, we can see that by importing torch, that's how I can create torches or tensors or anything that I need, right? Well, I want to check what version of PyTorch it is that I've installed. So I can go into the underscore underscore version underscore underscore attribute of torch. And by pressing enter, or excuse me, I got to close my quotation marks first. And now by pressing enter, we can see that Python is being executed. And now that it's done, it tells me, hey, 2.3.1 is the Python version, right? So I've just executed some code in Python. To see it in layman's terms, I could do something like -c, print, hello, X-ray. And it still gives us hello X-ray in the terminal. Go ahead, Tim.
I'm sorry. This is something you would do probably when you first come into a new Python environment that you're not familiar with to see the status of what version it's running.
So you definitely can. All I'm doing here is I'm compiling the following code in Python. I just want to ensure that I was able to install Torch into my virtual environment successfully, and that I could check the version that I currently have. Right? I'm just doing this to make sure that my installment worked correctly.
So is Torch named something different for a different Python environment? Say from 2 to 3.
No, it would still be named the same way if I installed it, right? So to give you a better example, so here's my actual machine, right? My
Yes.
local machine. If I do C, print hello, and I execute that, it gives me hello, right? But if I try to do something like import torch, and then I print torch dot underscore underscore version underscore underscore, and I try to send it, it's going to tell me, hey, you don't have anything named torch, because inside of my local machine's Python, I never installed torch, right? I only
Which makes
installed it
sense.
within my virtual environment.
Yes. Which is called what? Can you show it again for me?
The virtual environment is learning model EMV
Ah,
or
yeah,
LM.
there it is. Thank you.
Of course. All right. Awesome. So I see on the chat we have a couple of a bit of good information being shared. That's actually really good to know and I'm sure other people would be interested to know about it, especially Windows users, since you guys are the ones that are gonna mainly interact with CUDAs. For us in the Mac world, we're utilizing a completely different system that it allows us to run these GPU informations. Erica, if you want to share this knowledge, I recommend that you put it inside of the X-Ray public or maybe some sort of X-ray resources that the class president has created. All right. So moving forward, we have PyTorch. It is installed. I have the correct version of PyTorch installed, and I'm almost ready to start writing some code. Well, now I could write code in just a regular Python file, but what we're working with now is data, and we're doing essentially some I don't want to call it exactly scientific research, but we are doing some data research and some data manipulation. So something that's really useful for this specific topic is Jupyter notebooks. And we haven't touched Jupyter notebooks before. And what Jupyter notebooks actually do is they enable us to, one, write Markdown, and two, create Python code within the same file. That's extremely useful because you can add actual explanations, you could add documentation in the same exact file in itself. And the way that it compiles code, well, you can control that. And you could actually manipulate the code manually every single time rather than just having one solid script being pushed up. Kind of like a playground or a sandbox. Well, how do we do that, right? How do we get Jupyter notebooks installed? Well, the first thing is we're going to actually install Jupyter. So I'm going to say, go ahead and pip install Jupyter. And I'll go ahead and share that as well in the X-Ray questions channel. So now Jupyter is being installed. We can see this is a faster installment here. A very long one, but faster. And then after that, because I'm going to be utilizing Jupyter notebooks in VS Code, there's an extension that I'm going to actually grab so that I can use it. I'm going to click on the extension tabs here inside of VS Code, come over to my search bar, and go to Jupyter notebooks. If you just type in Jupyter, it's going to pop up. Just got to give it some time. Jesus. Maybe I have a bad internet connection, and that's why this is taking so long. I apologize, everyone. Tim?
I've had the same issue before with Jupyter. Most of the time you have to restart. Just do code dot, restart your VS Code and load it. The
Yeah.
first thing you do is load that and then it'll work. I don't know why. That's how I got it to work for me.
Awesome. All right. Well, it looks like I just had to close the extensions tab and open it up again. Sometimes that will do the trick. All right. So there it is, Jupyter. It comes up. We have Jupyter here. I think if I click on it, it's going to bring me to a site. It did. I'm going to go ahead and send a link here as well to Jupyter itself. All right, so here's a Jupyter notebook extension. You can see that I already have it installed. So you'll just come here and install this extension. And then finally, we'll need a way to actually run Python code inside of our Jupyter notebook. You may think to yourself, well, that doesn't make sense. I already have Python, and what I'm going to be executing is Python code. So why do I need anything to be able to execute Python code? Well, it's not necessarily the Python in itself that we need an adaptation to. What we need an adaptation to is how this file is being read. We need a separate kernel that is able to read this file utilizing specific directions. And what I mean by that is, like I previously mentioned, you can execute blocks of code at separate points in time rather than just the default, of going from top to bottom. So we need to make a separate installment telling it how to interact with our Python code. And I saw a hand go up. I'm going to finish this installment, and then afterwards I'll open up for questions before we go into creating our first file. So I'm going to go ahead and say pip install IPY kernel. And this is what we're going to utilize to actually interact with our Jupyter notebook code. See, IPY kernel. For me, you can see that it looks like I already have a couple of these requirements already satisfied. You may as well. It could be possible that when you install Jupyter notebooks, it already installed the IPY kernel, but it's never a bad idea to run that specific line of code just to ensure that you do have it. All right, before we go into opening up our first Jupyter notebook file, does anyone have any questions about everything we've done so far? I see a question from Momo.
Yeah, just I want to know the extension. Which extension you picked for the Jupyter?
It's in X-ray questions. I shared a link to it. You'll be
Okay,
able to
thank
see
you.
it there on Slack, of course. All right. So let's finish off this process. All right, let's go ahead and create our file. I'm going to run touch. This is going to be my name, which in this case, the name that I want is Tensor Playground. And then I'm going to finish off my extension. I'm not going to utilize py because that's just a regular Python file. Instead, the extension that I'm going to use is IPYNB, which stands for Jupyter. What doesn't stand for it, but it's going to open a Jupyter notebook file. All right, so I'm going to go ahead and run touch. We can see that a file was created. And if you look at the left-hand side, I already have a little icon telling me, hey, this is a notebook. And there you go. I am within Jupyter notebooks. All right. Well, let's go ahead and connect our information here. Just like I did before, I did a print statement where I import torch, and then I do print torch dot underscore underscore version. All right. Well, there's my information. If I click on this play button, nothing happens. It's not compiling my code. I'm not getting any sort of print statements. I'm not getting anything on the terminal. What's going on here? Well, oh, go ahead, Erica.
That's just the import of the library.
Yes, that's correct. I have the import of the library, but this print statement's not showing up, right? And that's happening because I haven't selected a kernel yet, right? Do you remember how we installed that IPYNB kernel? Or excuse me, not IPYNB, it was IPY kernel. We need to select a kernel for a file to compile, or for this Jupyter notebook to be able to compile code. Well, I'm going to do that by clicking on Python virtual environments. From there, it's going to bring up a series of options, right? Typically, you'll see your virtual environment here at the very bottom. In my case, I don't see my virtual environment. And it tells me, hey, you could create a path. Well, I don't necessarily want to create one. Let me see if I click on create here. It's going to tell me, well, which one would you like to use? That's not what I want. I'm going to go to Python virtual environments, and we can see here that it's just taken in paths, all right? Well, I can specify path. I can say the virtual environment that I want you to utilize for my Python version is within environments. And it's called LM EMV. It is within bin, and it is my Python 3 script. Doesn't seem to be accepting it. I may have to close this down and restart it. Let's see. It's not letting me find my correct environments here.
I just put Python without the extension and it just defaulted to the latest one.
Yeah, but that's not what you want to do, Erica. Because if you do it like that, it's gonna take you directly to yeah. See, so in my case, if I go to Python directly, it takes me to the one installed inside of my actual machine. So I may have to find a way to tell this. So the first thing that I'm going to do is I'm gonna go to Pith or Command Shift P. I'm going to choose an interpreter path. In this case, I want it to go, oh boy. Let me go back one here. Let's see if I have it. Okay, I don't. So I'm going to enter my interpreter path. Going to go to tilde/environments/ .lm env/bin/python. And I believe that will do it. Okay, so that sets my Python interpreter for here. Let me make sure that it did work. Okay, yes, it did. So I do have my Python interpreter. And now if I go to create, select a kernel, we'll see that the first one that pops up is my lm env. All right, it shouldn't be that complicated for the rest of you all. I just had some misbehavior happening from VScode. To do a quick summary, and I'll make sure that this gets added into our curriculum as well. I typed in Command Shift P to open up the command palette. From there, if you type in Python select interpreter will pop up. This is telling VScode which Python interpreter it is that I want to use. If your virtual environment does not populate in these options, you could click on Enter Interpreter Path. And from there, you just type in the path to your virtual environment, which in my case, it was environments/.lmenv. Inside of the bin directory, I had a script named Python. And that is what I passed into my VS Code. This tells VS Code in itself which Python version to use, but it does not tell my kernel which Python version to use. So you have to click on kernel and then select your virtual environment. All right. Well, now that I went through that entire process of trying to figure out how to connect my virtual environment to my Jupyter notebook, I can click on play. And now it's able to execute my Python code and print my torch statement of 2.3.1. Right, and now I can add a little bit of markdown saying, yay, I've installed PyTorch successfully. And there you go. We can see that I have some markdown code saying, yay, I've installed PyTorch successfully. PyTorch is able to be called from my virtual environment, and I'm able to execute my Python code within Jupyter notebooks. All right. At this point, does anyone have any questions regarding the installment of PyTorch? Okay, it doesn't look like anyone has any questions. In the second portion of our class, we're going to be going over tensors and how to manipulate tensors. So it's important if anyone is trying to follow along that they do have PyTorch installed. So from now until 11 o'clock, I want everybody to go through the curriculum and ensure that they are caught up to me and they have a Jupyter notebook opened up and they are actually able to execute some PyTorch code. I'm going to go ahead and stop our recording here. All right, welcome back, everyone. In part 2 of our lecture today, we're going to be discussing what is a tensor or what is a torch tensor. All right, well, everything in learning models is in the learning models that we're going to be building is going to be tensor related. Now, in a tensor is essentially just a multi-dimensional array or a multi-dimensional list, right? Otherwise called a matrix. Let's go ahead and build one so that we can see what it looks like. I'm going to go ahead and say, I'm actually going to import here. Oh, this is markdown. Excuse me. Let me take that off. Oh, we do want markdown. I'm all cross-sighted. I apologize. Let's go ahead and do that. Let's say building or Python matrix. We're going to go ahead and build a Python matrix or a matrix utilizing only Python, right? So here's my markdown file. It's good to go. I'm going to go ahead and write some code here. I'm going to import random to be able to create this matrix. And there's a couple of different ways to do this, right? I could have my matrix be equal to an empty list, and I can say for, I don't know, in this case, let's just do IDX in range 3. And all I want to do is have inner list be equal to that. And now let's go ahead and say for IDJ or JDX in range 3, I want inner list to append a random number. All right, and at the end of each loop, I'm going to go ahead and say matrix dot append inner list. So this is going to give me a list of 3 separate lists nested within it with 3 separate indexes at each level. But let's take a look at it just so that we can see it. Let's go ahead and let's see, how do we want to do this? I'm going to simply make this an F string for visualization purposes. And what I'm going to print will be matrix at index 0. I will then print matrix at index 1. And then finally, we'll print our last matrix at index 2, or a last list inside of our matrix. I see a question from Chris. Give me a second here. After we visualize this, I'll go ahead and open up for questions. All right. Well, when I run this Python code, here we can see that this is what my matrix looks like, right? I have a list of lists, right? Where each one is containing a random float number between 0 and 1. That's all I'm doing here. And I'm creating this list of lists, right? Now, I created this utilizing purely Python. There's definitely a cleaner, more syntactical way to do this. What we can do is, rather than having all this gibberish of different for loops happening within one another, we can utilize list comprehension to say, I want a list of random.random for, and I'm just going to do underscore because I really don't care what it is being called. And I want this to happen for in range 3. And when I execute this information, we'll see that it still gives me back a random list being created every time. Right? So everything is there. Just creating a random list. Rather than writing all of this gibberish, I've made it into a more of a cleaner syntax where I have 2 for loops, one nested within the other, creating a list of lists. That's all I'm doing. This is all a matrix is. It is just a list of lists, and that's what tensors are going to be represented as. All right, I'm going to go ahead and open it up for questions here. I saw a question come up earlier. I think it was from Chris.
Yes. Were we supposed to be following along, like with code or anything, or should we just be watching?
That's definitely up to you. You could follow along or you could watch. I recommend that you watch for this go around. The purpose of the last hour block was to ensure that everybody had a good working environment before this afternoon.
Got you. All right. Thank you.
Of course. All right. So there you go. I was able to create all of my code and I have my list of lists. But when I run into a list of lists, I run into a couple of issues, all right? Especially if what I'm trying to do is a considerable amount of math operations and I want them to all happen pretty quickly. Well, let's talk about some issues with Python matrices. Right? Well, if I wanted to add, what would I need to do in order for this function to work, right? I want to add 2 random matrices. Let's say I have matrix 1, and let me just put 1 on all these. And I have something called matrix 2, right? What would I need to do in order to add matrix 1 to matrix 2? Not only do I want to add it, but I want to add it by index, meaning that the index 0 of my first list should be added to index 0 of the second list of matrices, right? So I have my first matrix where at index 0 of the first list is being added to my second matrix of index 0 of my first list, and so on down the line. Well, how would I have to build that function in order for it to work properly? And I'm not asking about writing code, I'm just asking about some pseudocode here. All right, let's hear it, Ruben.
Could you use a dot map function?
Yeah, I could use a map function. And I would have to essentially have 2 functions nested. Let's go with a for loop here. Let's just say iterate through, would I iterate through only one of the matrices or both matrices? Raven?
Oh, it'd have to be both.
Yeah, so I would iterate through both matrices first. All right. And after iterating through both matrices, I could then grab each index and add it together, right? Well, now, there's a couple of issues with this method or this functionality. There's edge cases that we would have to consider, right? For example, if one of these were to be blank, one of these fields were to be blank or null or none in Python, right? They don't exist. Well, trying to add a none value to a float number would raise an error, right? So I need to ensure that within my loop and validating the type or input and writing a default statement in case types don't match. And what if one of my 2 matrices wasn't the same length, right? What if matrix 1 was in a range of 3 matrices, but in matrix 2, instead of having the same size, I have one that is still 3 list within it, but it only contains 2 elements for each one. Well, my iteration would have to be handled in a different way, right? I would have to account for an edge case where the shape of both matrices don't match. Right, so there's quite a bit of complicated stuff that goes into it. And writing all of this Python code straight off from scratch, sure, we can do it. It may take us a little bit of elbow grease, but we can definitely do it. But when we have PyTorch and when we're talking about a considerable amount of data that we're going to be handling and conducting different sorts of mathematical operations at each level, because right now we're just talking about addition, right? But what if we have to also calculate averages? Well, we have to calculate means, subtractions, divisions. Well, all of these edge cases may change, and depending on which mathematical operation it is that I'm running. And what we end up with is a massive function that we would have to write from scratch. Well, that's not what we want, right? So, because that's not what we want, somebody came up with the idea of, hey, let's just create a framework that will handle all of these mathematical operations straight off the back, right? It will create a tensor in a much friendlier format, or a much easier way to create a tensor. And it will actually run these operations and handle these edge cases for us straight from the get-go, instead of having the developer have to go through that. So that's where PyTorch comes in. So now we're going to go ahead and build a tensor utilizing PyTorch. And we'll go ahead and conduct some mathematical operations here. All right, so I'm writing all of these notes here at the same time that I'm actually going through and creating the demos and notes, which is super handy. All right, gonna go ahead and add some code here. I already have Torch up above, but what I want to actually utilize is something called Torch Tensors. So you could just do torch.tensor, but for simplicity's sake, just so that I don't have to continuously type it over and over again, I'm gonna go ahead and state from Torch, I want to import tensor. All right, now let's go ahead and take a look. And I'm going to run into an issue here on purpose so that we can visualize how the Jupyter notebook is interpreting code here. So I'm going to go ahead and create a tensor. And I'm actually going to wrap this very first tensor right out of our demos and notes, just so that we don't have to type it over and over again. Let's see, tensor, don't need the torch part. All right, so there we can see my tensor is being copied strictly from our demos and excuse me, not from our demos and notes, our curriculum. And when I click on this play, I'm going to go ahead and get an error saying that tensor is not defined. All right, so there you go. I clicked on play. I get tensor is not defined. Well, I definitely have it here, right? I said from torch import tensor, but I'm getting a tensor is not defined down below in my script. Why could that be happening? Does anybody want to take a guess? Let's hear it, Dustin.
You need to run that cell.
Awesome.
Above.
Yeah, thank you. So this does not work the same way that my Python files or my Python scripts work, right? It doesn't start from the very top to the very bottom every single time. It only occupies spaces in memory for things that have been played or executed. This was executed one time before, but I then added this statement saying from torch import tensor, but this is not part of my memory yet. I need to execute it again. Now it's been executed. And it's telling me the step. Look at that. It's step 7, 5. And here was 6. Well, now when I run this, it will turn into step 8. And now it's actually able to identify tensor and show me the values for my independent tensors. Right? It's showing me, hey, this is a tensor type. When I went ahead and printed it, and it shows me the values for that multi-dimensional array. All right, so my matrix has now been built. Let's go ahead and talk about this issue of addition that we discussed the first time. I'm gonna go ahead and make this matrix 1. Gonna overwrite that space in memory. I'm gonna grab my second matrix here. And I'm changing these for matrix over tensor because, as you all know, we now have tensor as a keyword. So I want to make sure that I reserve that and I'm not utilizing it for a variable naming type. When you conduct these additions, you'll see that they'll all evenly add up to 10. Now I want to add matrix 1 plus matrix 2. Well, what's going to happen when I execute this code, right? I'm not necessarily going through and iterating through both of these. So I wouldn't expect it to just be able to do element-wise addition. And as we know before, if you try to add a list plus a list, all it does is concatenate the list and stretch it out or raise an error, right? Well, when I do it here inside of Tensor, I'm not actually messing with a list. I'm not manipulating a list here. I'm manipulating a tensor. So it has different behavior. By running this addition, it is conducting element-wise addition, right? It's able to add 1 plus 9 and so on. It would do the same thing if I try to do subtraction. All right. So we can see how our mathematical operations are now simplified by just simply utilizing a tensor to represent our matrices rather than utilizing a multi-dimensional list. All right. At this point, does anyone have any questions as to why we would utilize tensors, how to build a tensor over a multi-dimensional list? Mikkel?
If the tensors aren't of equal length, what happens?
Yeah, that's a great question. Let's go ahead and try that out. What's going to happen if my tensor is not of equal length, right? Going to go ahead and try to add this. Look at that. It tells me, hey, these tensors are not of equal length. And it tells me straight off the bat. It tells me, hey, this tensor A, which is of size 3, must match the size of tensor B, which is of size 2. And it tells me non-singleton dimension of 0. So it's before having to iterate or trying to write these edge cases, it's already accounting for that 0. And we'll be covering over how to compensate for this kind of size difference later on when we go into mutating tensors and other lectures during this module. Does that answer your question, Mikkel?
Yes.
Awesome. All right. Any other questions? Let's hear it, Gary.
Yeah, so can you just go through the math one more time? So you're adding matrix 1 and matrix 2. I see the result and then
sorry, maybe I didn't understand your question. You said go through, you want me to go through the math?
sorry, I was just looking at like what can you go through real quick just what's happening here? Just so I could have it locked in.
Yeah. So essentially the first time we did it with actual Python nested lists. We were building these matrices manually with just purely Python code. And if we were to do an addition, we would have to iterate through each one and add them together. Well, when you're doing tensors, it's doing element-wise addition, meaning it's identifying the first list of each one of the matrices and grabbing the first element of each one of the matrices and then adding them together. So 1 plus 9 ends up giving us 10 in the first matrix, 2 plus 8, 10, 3, 0, 10, and so on down the line. And that's how it fields that final third matrix. Does that answer your question, Gary?
It does. Thank you.
Of course. Mikhail?
You said before when you imported the tensor, it
Mhm.
has to be loaded in memory for it to be able to be used. So if you open up a new file, would you have to like run all, or like can you run individual code block sections? So if you import that tensor from a different code block section, in order for it to be utilized, you have to load it in memory before it will be utilized. It's a new
Right.
file.
Right. So if I were to open up a new file, I would have to run these import statements again. And anytime it gets used somewhere within my file later on down the block, I have to ensure that this has already been executed so that it's saved into the memory.
Okay.
All right. Awesome. Do you have another question, or is that just a glitch?
That was. Oh, I'm done.
Okay, awesome. All right. So now that we talked about adding this information, we can see how PyTorch tensors can give us some really useful tools, and it makes it essentially just extremely easy to interact with this massive amount of data that's being represented as tensors, right? Well, now let's take a look at a couple of the methods that come in with tensors. As we discussed before, a tensor is going to essentially represent each individual neuron in our learning model, right? Well, now let's go into how we can manipulate these tensors real quick. We're going to talk about reshaping a tensor here. So we already have matrix 1 and matrix 2. Let's go ahead and add some markdown here and say, hey, this is going to be my reshaping section. Now I'm going to add some code. Oh, hello. Mess these two up. Let me go ahead and okay. There you go. Shift them around real quick. All right, so for reshaping, I'm gonna grab matrix 1. And all I'm gonna do is change the way that we see it, right? Or its actual shape. I'm gonna say reshaped matrix 1 is equal to matrix 1 dot view. Let's see what happens when I do 1 and 9. All right, let me go ahead and print matrix 1. And now I'm going to print reshaped matrix 1 so that we can see it. Look at that. So the first shape of my matrix was of 3, right? I had 3 list with 3 indexes. So it was a 3 by 3 shape. But I changed my view so that it would be 1 specific list with 9 indexes. And you can see that it took the following 2 tensors and essentially just concatenated it all to just be 1. Right? It grabbed those 3, compiled into one another. This is not going of a series of 1 through 9. It's grabbing the numbers down below and putting them together. Maybe I need to change this code a little bit so that we can visualize it better. Let's do double 5s and let's do some double 7s here so that we could see it. All right. All right, so there we can see our 1, 2, and 3 corresponding to the first tensor. Here's 5, 5, 6 corresponding to the second tensor, and then 7, 7, 9 corresponding to our third and final part. All right. And that's how we were able to reshape that tensor to turn it into a 1 by 9 dimension. Does anyone have any questions regarding reshaping? Okay, so let's go into slicing. Now, slicing is going to be a little interesting because it's not exactly what we're used to. I'm going to go ahead and open up another markdown block here. Say, hey, we're going into slicing now. Save that, open up a code block. And in this code block, I'm going to say my tensor. There's the tensor that I want to build. All right, it's just 1 through 9. Nothing crazy. If I run it, it executes pretty well. Great. Well, now typically what I'm used to when I go ahead and slice a list is, well, I just grab my original value of my tensor and I specify in parentheses, hey, I want to do something to this. I'm going to give you the initial value, right? Which let's say my initial value is 1. I want to go all the way to the end. So it should give me these last 2 tensors. All right. Well, let's print it and see what it does. So now print sliced tensor. Well, it works, right? It's able to give me that information. That's great. But what else can I do here, right? Other than just slicing by indexes, well, I have nested list. So maybe there's something else that I can do here. Well, I can add a comma and specify which one I want, right? So let's say I go into 2. Well, now it just returns the index 2 of the last 2 as a tensor, right? So here we go. I said, hey, I want you to grab index 1 and to the end. So I grabbed my first list, my second list of 4, 5, and 6, and my last list of 7, 8, and 9. And then it only grabbed the last 2 elements. It grabbed the number 6 and the number 9 and created a purely different tensor from that, right? That just says 6 and 9. So it gives me a little bit of an option to be able to manipulate this. This is also what you'll see when you're working within NumPy when it comes to manipulating the different NumPy arrays that come back. This is a NumPy functionality that PyTorch is just mimicking or adapting. Actually, I'm pretty sure under the hood, it's just running NumPy as well. Right, I can switch this to say, hey, I only want index 1, and that should return 5 and 8. And I can also say, well, I only want index 0, and that would return 4 and 7. All right. Questions? Oh, let's hear it, Chris.
Can you re-explain that again? So the first number is the index, and then the second number is what again?
Yeah, definitely. So this first argument is working just like normal, right? I am just grabbing or slicing a list. I want from index 1 till the end of the list. I could also say I want from the start of the list all the way till index 1, right? And then stop at index 2. That would also work. When I run it, we can see it gives me 1, 2, 3 for the first index, and then 4, 5, 6 for the second index.
Okay,
Right?
it's a range. Okay.
Yeah, so that first portion works normally like we have in Python.
Okay.
Now, when I place in that comma, I can grab a specific element from within these 2 that I've chosen. I can say, hey, I want you to return index 1. Well, index 1 of this list is the number 2.
Right.
And index 1 of the second list is the number 5. So when I execute this, it would return 2 and 5 as my tensor.
Why didn't return 8? Is that not the index 1 itself for the third portion, the 7, 8, and 9?
Yeah, so 8 is another index of 1, but remember that I'm cutting the list up to
Gotcha.
index 2.
Got you. Okay, thank you.
Of course. Brandon?
Can you do further slicing with the second number?
Yeah, let's try that out. All right. Let's say that I want to do further slicing with the second number. Well, let's see if I could grab from index 1 all the way to the end, right? When I run this, we can see that it's also slicing as well, right? It grabbed 2 and 3 for the first list, and it grabs 5 and 6 for the second. Does that answer your question, Brandon?
Yes, it does. Thank you.
Of course. All right. So there's our slicing. Specifically in Tensor, we have something, or specifically in NumPy, we have something called a Boolean indexing, right? Now, this Boolean indexing works where we can specify a condition and it would return only the numbers within the tensor that does meet that condition. So let's take a look at that. And I'm going to actually separate them all together. I'm going to call them Boolean. Excuse me. Go ahead and add that here. Boolean slicing, which is just a conditional. It's an if this or not, right? If it does meet this condition, this is the specific tensors that I want you to return. Well, let's run that. We still have my tensor. Let's say Boolean tensor. And what I'm going to do is I'm going to grab my tensor and say, well, I only want you to return this information back for every tensor that is greater than 5. And then I can print my Boolean tensor. All right. Well, now we can take a look there. It returned one solid tensor. All right. It's not necessarily slicing the way before where it returned multiple lists. I am just creating one solid tensor for all of the elements within it that were greater than the number 5. So we see that it returns 6, 7, and 8 back as its own independent tensor. And that's Boolean slicing. It's just saying it's a conditional. Any questions regarding slicing? All right, let's hear it, Brandon.
Actually, use this logic in just like raw Python. Like, can you call an array with a conditional index like that?
I don't believe so. Let me go ahead and I could try it out. I might have to entertain it afterwards. Yeah, because I'm getting squeezed on time.
No worries.
Thank you. All right. The next thing that we're going to be looking at here is going to be concatenation. Oh man, I cannot spell that. Let's see. There you go. All right, so concatenation. Now, typically what we're used to is saying, hey, a string plus a string, right? If this was SS, well, this would return to us SS. And if I had a list of S plus a list of S, well, that would return to us S. Oh, that's supposed to be a comma. All right, so we've seen concatenation before. But as we saw with tensors, when I add them together, it just conducts index. Oh, that is supposed to be that. There you go. It just conducts index level addition, right? So if we try to do something like this information in a tensor, well, what it would actually return would be a list of 2 S's, right? Because it would add them together. So it's not doing exactly what we want. Well, sometimes we may need to actually concatenate. So in order to concatenate 2 matrices together, it gives us a specific function called concatenation. I'm just going to go back to matrix 1 and matrix 2. I'm going to grab them and bring them back down just so that we could see them here. They already exist within memory. I do not have to do that. I do not have to grab them and bring them back down. I'm doing it so that we can actually see it within the code block. All right. I'm going to go ahead and say, well, I want to concatenate. I'm just going to say conc matrices. What I'm going to do is I'm going to grab the tensor that I want to come first, or the information that I would want to be represented first, which is matrix 1. And I'm going to then concatenate. Oh, excuse me. I'm going to call torch, then call the concatenate function. And I'm going to specify I want to concatenate matrix 1 with matrix 2. I am then going to print this variable. Whoa, there you go. And when we run it, seems like I get a bit of an issue here. Let's see. Cat receive an invalid combination of arguments, got tensor, but expected one of tuple of tensors. Let's see what happens if I add this last argument here. Yeah, it still gives me the same error. Let me go ahead and grab the code block that we have specifically. All right. Not exactly 100% sure why it didn't work with the original code. But here we see we have tensor 1 that is being created. It is just a tensor of 2 elements. All right. We see tensor 2 being created, which again is a tensor of 2 elements. And when I utilize the concatenate function, it's able to grab them all and concatenate them into one massive tensor of 4, right? So it's a 1 by 4 rather than being a 1 by 2 for each individual tensor. And that's concatenation. Does anyone have any questions regarding concatenation? Let's hear it, Chris.
What's the dim equals 0? What is that representing?
Yeah, so this dim equals 0. Oh, I apologize. This dim equals 0. It stands for dimensions, right? We could change it to 1. And we could see that by changing it to a 1-dimensional, it still concatenated our information, but it concatenated it in a separate direction, right? Where it grabbed index of 1 and mixed it with index of 1 down below. And then it grabbed index of 2 and mixed it with index of 2. So that's what dimension 1 stands for. Dimension 0 means, hey, we have no dimensions. Just concatenate these two lists. Does that make sense, Chris?
Yes, thank you.
Of course. Any other questions? All right. So let's go ahead and move forward here. The next thing we're going to be talking about is going to be stacking. Hello. Nope, I didn't mean to do markdown. There we go. Code. All right, so stacking. Let's go ahead and write this code out. So I want to stack two tensors together, right? I have tensor 1 and tensor 2. Well, how could I stack them? All right. Well, let's go ahead and print torch dot stack. Again, I'm going to grab tensor 1 and tensor 2. And I'm going to specify a dimension here. And for now, let's do dimension 1. All right, so we're still manipulating tensor 1 and tensor 2. And let me actually grab them and put them within the same code block, just so that it's all isolated. Argument tensors, position 1 must be tuple. Let's see, looks like we're getting that same error that we had before. Let me try
I
this
believe
out
it's the-
real quick. Oh,
It's the parentheses on there. In your print statement.
oh, I had a bad print statement. Yeah, I do. Thank you. Thank you, appreciate it. Go ahead and run that syntax. All right, so there we see there's a stack, right? So this is different than what I had up here, right? Where if I give it dimension 1, it returns to me 2 nested tensors, right? Or excuse me, 2 nested lists within my tensor. We see 1 up above and 1 down below, right? Where it's 1, 2, 5, and 6, 3, 4, 7, and 8. Well, in this case, I'm not just mixing them together or concatenating those two, right? Down below, I'm actually just stacking them to be nested within another level, right? So now list 1 has 2 children lists of 1 and 2 and 5 and 6, and list 2 has 2 children lists of 3 and 4 and 7 and 8. So that's the difference between stacking and concatenating. All right. Does anyone have any question regarding our tensor manipulation up to this point? All right, if there aren't any questions, we're going to go ahead and move into our tensor methods now. Now, tensor methods are just like everything else. We have a lot of built-in methods that have separate functionality to show us different things of our tensors. So I'm going to go ahead and bring some of our matrices back. Let me grab matrix 1 and matrix 2. I'll grab tensor 1 and tensor 2 as well. And finally, we don't actually, that would be a good one to show as well. All right, so here's all of our different tensors that we've created so far. Let me go ahead and take care of that there. All right, they're all within their own nested information. And they all work properly, right? I can click this play button. There's not going to be an error. All of my tensors is being created. Well, let's talk a little bit about methods here. And for this methods, instead of writing Markdown, I'm going to go ahead and add some comments here. Oh, hello. We're not in JavaScript anymore. So let's talk about some shape and sizes of our information, right? I'm going to go into tensor 1, which I believe will be the easiest one to visualize. And I'm going to print the shape attribute. But when I run this, it tells me, hey, tensor 1 is a tensor that has 2 lists inside of it. And both of these lists have 2 elements within it. All right. If I were to change this over to matrix 1, it would tell me matrix 1 is a 3 of 3. All right. So I'm going to go ahead and execute this. You can see matrix 1 is a torch size of 3 of 3. Well, now, what about a separate method here, right? Let's print matrix. Actually, let's go back to tensor 1 dot size. Well, tensor shape, when I ran the shape of it, it was returning me the size. So what does the size function do, or what's the difference? Well, when I run it, right, it's still giving me the same exact information. It's giving me, hey, this is the size. If I go to matrix 1 and I try to call the size method, they're both running the same information and returning the same stuff, right? So this shape attribute is just calling the size method to grab the shape, right? It's two different ways of accessing it, but they're both returning the same information. Think about it if it was OOP, right? We have our getters and setters. Shape is an attribute, and its getter is the size method. So it calls the size method to be able to grab the information. All right. Any questions regarding shape? Okay, let's go ahead and take a look at a different portion here, which is our numeric dimensions. And let's start off with the easiest one, which is going to be tensor 1. And let's go ahead and run .ndim. I'm actually going to comment that out here. Well, now it tells me, hey, the numeric dimensions are of 2. All right. Well, let's go ahead and see what happens when I run it with my tensor instead. Well, we can see that my tensor is also returning a numeric dimension of 2. And if I run it with something like a floating number, which is matrix 1, still just returns numeric dimensions of 2, right? So it's trying to evaluate the dimensions of each one of the numbers. If I had something more complicated, it would return a different answer. But for now, we're going to continuously see the numeric dimension of 2. I'll have to find a better example for us so that we can see different values that come from that. I'm going to go ahead and move into our data type, which will give us some important information, especially once we start working with the data that's coming straight out of CSV files. And let's start off by calling tensor1 dot dtype. This is telling me this is an integer 64. Okay, great. Well, what if I run this with something that's holding some floating numbers, like matrix 1? Well, when I run it through floating numbers, it's telling me this is floating number of float 32. Great. Well, what if I brought in some of my random information, right? Let's say I wanted to create a tensor that looks like this. Well, let me find the bottom of my file here. Let's say rand tensor, and that's equal to a tensor. And it contains the following, right? So there's my tensor now. I missed a couple of commas here. All right, now let's run it to the rand tensor and see what kind of D type it gives me. Well, you can see that it's returning float 32 for all of them. And for integer, it's returning integer 64, all right? Now let me go ahead and run this back to my tensor 1. There we can see our integer 64. So those are the two data types that we're currently messing with or currently interacting with. We're interacting with floating numbers and we are interacting with integers, right? We've seen it before where there's some other types of numbers or some other types of data types. And here we're going to be mainly focusing with floating numbers and integers. Now, why is this data type function important? It's because sometimes when you have integers, you may have to cast them into floating numbers in order to interact with the remainder of your data correctly, which we'll be covering on here shortly. Well, now let's talk about unsqueeze. Right? Currently, I have all of these tensors. Well, what happens when I try to unsqueeze a tensor? I have tensor 2 here. And if I go ahead and squeeze, if I go ahead and print tensor 2, well, that's just going to simply give me the tensor itself, 5, 6, 7, and 8, right? Well, if I run the unsqueeze function and try to grab this, well, it's going to return to me a different format. It's still going to return to me the different data. It's just going to be in a different format, right? I'm going to go ahead and run unsqueeze 0. Well, notice the difference, right? Let me go ahead and print them next to each other so that we have them. All right, so here's tensor 2. There's 1 parentheses there. And then after that, goes straight into our tensors, right? But in the tensor that we just unsqueezed, we actually nested it within another list, right? So first list, then data starts, first list, then we nested the list, and now we have our data, right? So we're just putting our data inside of another level by doing this unsqueeze function. All right. Does anyone have any questions regarding the unsqueeze method? Okay, if there aren't any questions, I'm going to go ahead and continue moving forward here. The next thing that we have is Ravel. Let's print tensor 1 and then print tensor 1 dot Ravel. Well, now with this is executed, it kind of changes the view, right? Just like before when we had the view function to reshape our tensors to be 1 through 9, this specifically just did it for us, right? Rather than having to specify the arguments, hey, I want this to be a singular for 9 elements, I just said Ravel and said, okay, so you want all of these to get wrapped up and turned into one specific row. Fantastic. The next one we have is split. Now split works as follows, all right? We're going to go ahead and do my split tensors be equal to tensor 1 dot split. Oh, hello. 1 and dimension 0. All right, I'm not necessarily trying to grab one number out of it. Okay, well, let's print this split tensors to see what we get. So now we can see that we have a tuple, right? Not a list, but a tuple of 2 separate tensors. And it works exactly the same. I could do 0, and when I execute this, it would only return the first tensor. Or I could do 1, and that would only return the second tensor. All right, this returns a tuple of 2 tensors by splitting it. All right. Now there is some built-in math operations here. Let's go ahead and go into math operands. And we're going to go ahead and go over the sum, mean, and max functions today. So let's go ahead and start off with tensor 1. Let's say sum tensor is equal to tensor 1 dot sum. Mean tensor, it's equal to tensor 1 dot mean. And then let's go ahead and go into our aggregation or our max function here. And we'll see what it looks like once we go ahead and print it out. Max tensors, which is a tensor 1 dot max, which has a dimension of 0. Well, now let's print it. Oh. Ooh, it all got typecasted somehow. All right. And then max tensors. All right, so there's the 3 types of tensors here. All right. I'm going to execute this file. Looks like I have a bit of a issue going on here with the mean. Let's see. Mean could not infer output D type. Input D type must be either a floating point or a complex D type. So it looks like it wants a floating point value. So for floating point value, it looks like the easiest one that I have to work with is matrix 1. So I'm going to go ahead and change all of these from tensor 1 to matrix 1. All right. Okay, so that worked correctly. Now we can see all of this being inputted out, right? Or all of our outputs. So now what we have here is a sum of 45. That is the sum of the very first tensor that we created in matrix 1. We have a mean of 5, which makes sense. They all add up to 10. So, and then we have our max tensor here. All right, our max tensor returns a type of 2 of them. It returns values and indices. So it looks like the max index was 2 for all 3 places, and the max value for all 3 lists was 7, 7, and 9. Now notice this is wrapped in a tuple, right? It's returning 2 values. So what I can do is I can either deconstruct it, where I can say max values, and I can say max indexes. And now I can actually print it out, where I say max, values and max indexes. All right, and it still gives me all the information. Here we go. The max indexes was 2, meaning that they are all of length 3, right? 0, 1, and 2. So it's telling me all of the lists or all of the nested lists within the tensor. They only go up to index of 2. And then my max values for each one says that index 2, the value that or the max value in it, it's not necessarily at index 2, but the max value out of all 3 of these indexes was 7 point, 7 point, and then 9. All right. Does anyone have any questions over these math operands that are come built in? It's here, Erica.
You can also try tensor sum item to sum all the items.
Tensor sum item, you said? What do you mean?
Yeah,
by-
dot item bracket, no brackets, parentheses.
Oh, like specify dimensions and stuff?
No, no, the parentheses in sum is empty, dot item. So it sums the items of the tensor.
Okay, so parentheses dot items.
With outside, it's dot sum, dot item. And then parentheses. Oh, it's parentheses in English? So parentheses. Sorry. Oh, but with tensor. And it should work with tensor too. Like instead of matrix 1.
Oh yeah, the sum didn't throw the error. What threw the error was the mean.
Oh, I think it's the same. It's just like if you specify it's the items, the tensor should work well too.
Yeah, let's try it out. Let's do tensor 1 and then dot item. Yeah, so it looks like that still throws an error.
It's using tensor 1.
Yeah, we'll have to take a look here. All right. So moving on, now that we've got all of our functions there and we can understand how to utilize some of the built-in math, let's go ahead and take a look at the transpons or the transformation function. All right. Well, let's see. We're gonna do this with matrix 1. So I'm gonna say print, and let me leave a comment here. And what I'm going to print within this function is going to be matrix 1 dot t. Oh, I forgot to comment all this out. All right, so notice it didn't really change anything. We still have 157, and let me just actually print matrix 1 so that we can see it. All right, so here we go. Here's 1, 2, 3, 5, 5, 6, 7, 7, 9. When we utilize that t functionality, boy, flipped it. All right, 1, 2, 3 are no longer my indexes at the top. They are my indexes from side to side. All right, 5, 5, 6 is now flipped. And 7, 7, 9 is now also flipped. All right, it essentially took my tensor shape and put it on its side. And that's what the transformation function does. Does anyone have any questions over any of the methods that I covered up to this point? All right. Now, all of these tools are not necessarily something that you're going to be utilizing every single time that you write some sort of learning model project. They are all tools that are good to have in your toolbox so that when you come across a problem, you can revert to utilizing these tools and applying them. Now, the last thing that we're going to talk about here are some scenarios, one of them being normalization. And the other one being broadcasting. All right. So now normalization, it just basically stands for, hey, I have a ridiculous amount of data, and I want to insert something new into the neural network, right? And I want to this new information that I wanted to import, I want to stretch the current data that I have. Well, how could I do that? All right. I don't want to create fake data that's just gonna mislead my model, right? I want to make data as accurate as possible. So instead, what I'm going to do is I'm going to, one, create my tensor that I want to add. All right, I'm gonna make this my tensor function. This is gonna be nested of 1.0, 2.0. Then we're gonna have 3.0 and 4.0. And so there's my nested. I can go ahead and print my tensor, and everything works correctly. All right, there's my tensor. It's been built. Well, I want to make sure that my tensor is normalized. So let's check this std function, right? What does that stand for? Or what does it do? Well, it tells me, hey, this isn't going to work because we only support floating points or some complex information. So if I were to reference back to something a little bit more complex, like my rand tensor, and run this std function here. And then execute it. Well, we can see that it provides me the standard, right? A standard of what all of those random numbers accumulated to, right? And it looks like the standard is 0.3134. And let me scroll up. This is the tensor that we're currently working with. All right, it's coming up to a standard. Now, that's great to know, but let's see if I can normalize this tensor. We don't expect anybody to memorize this off the top of their head. What we're going to do is we're going to take my tensor. We're going to then subtract this tensor from the tensor mean, or we're going to take the tensor mean away. Give me a second here, Cody.
Sorry, you just misspelled tensor. You're pulling the other tensor from up top. You don't have the N in that one.
Ah, thank you.
Yeah.
Right. And from there, we're going to go ahead and divide this. Nope, excuse me. We're going to divide the result of that subtraction by the tensor, or excuse me, by my tensor dot std. All right. So now when we run this, we can see that that all ran correctly. All right. Let's go ahead and print it out. Let's do normalize tensor. Well, now I fed it some data, right? And it went through the process of identifying the mean of the data. It subtracted it from each one of them. That's how we ended up with some negative numbers. And then we normalized it by dividing it through the standard. And that's how we ended up with this tensor being a little bit more valuable as to what our normalized data should look like. Right? If you ever have something that's like, let's say you're collecting massive data, but all of a sudden you have an abruption or someone's not following the common trend that you're collecting, you would want to normalize that data and before you feed it into your model. All right. Now, the second thing that we have here is broadcasting. And in broadcasting, all we're essentially doing is we're matching some dimensions here. So let's go through that portion here. All right, let's say single view is equal to a tensor that is 1.0, 2.0, and 3.0. All right, so there's my single tensor. Well, what if I have a 3 view tensor? And this tensor is 1.0. And I apologize, I need a nested list here. So All right, I have another tensor saying 2.0. And then I have a final tensor stating 3.0. So one tensor is a 1 by 3, or right, where my other one is a 3 by 1. Right, so there I have two tensors being located, a 1 by 3, and the other is a 3 by 1. Well, let's say that I wanted to add these two together. All right, we have my single view plus my 3 view. Well, what would that do? Well, they weren't the same length, right? So I wouldn't expect them to be able to conduct some sort of addition. And I do still have my elements being applied here, right? I still have my final view that was being placed out came out as a 3 by 3. Well, how did that happen? Right? I'm only adding. It's not like I did something complicated. And it's able to do it to where two tensors are not of the matching length, but they do have a matching number of elements within the parent tensor. So how did that work? Well, what it did is it grabbed the very first tensor, which was 1. It added 1 plus 1, that gave me 2. 1 plus 2 gave me 3. And 1 plus 3, that gave me 4. It then moved on to the second tensor. 2 plus 1 gave me 3. 2 plus 2 gave me 4. And then 2 plus 3 gave me 5. And then it finally moved on to the third and final tensor. 3 plus 1 gave me 4. 3 plus 2 gave me 5. And 3 plus 3 gave me 6. All right, so it grabbed each nested list and applied the addition to each of the elements from the single view tensor. Right, it essentially conducted where now my 3 by 1 mixed with my 1 by 3. Well, if I put those three together, 1 times 3 is 3, and 3 times 3 is 3, and gave me a 3 by 3 view. All right, and that is broadcasting. Does anyone have any questions regarding any of the methods that we covered today? Let's hear it, Raven.
For broadcasting, you said it takes the parent. Is it the parent just established as the bigger tensor?
No. So what I mean by the parent, right? If I were to break this up to be a little bit more visually appealing. All right. This pink bracket on the outside, that is the parent, right? Is this pink bracket on the outside of our tensor. Now, it took this tensor down below, which is 1.0, and conducted the addition to each element and added it to that tensor, right? So it took 1, added 1 plus 1 to grab 2, 1 plus 2 to grab 3, and 1 plus 3 to grab 4. And it stretched out that initial tensor to then become the first row down below. Does that make sense, Raven?
Yep, so basically it's just taking the inner list, so if it has a bracket. Okay, gotcha, thank you.
Of course. All right, any other questions regarding tensor manipulation? All right, if there aren't any questions, today what we covered was virtual environments, how do neural networks work, and we'll go further in depth into each step of the neural network as we continue building out our learning models. We covered how to install Jupyter notebooks. We covered how to install PyTorch, and then we went through some of the tensor methods, what they do, how they can help us, and how we can apply them. Does anyone have any questions over anything that was taught today? Let's hear it, Brandon.
Look at things other than numeric values with this kind of stuff.
Are you
Or any
saying? Oh, go ahead.
like any type of like visual representation, because it feels like we're going over like tensor manipulation here, but the numbers don't really do anything for me. Like they're just numbers that we're rearranging or manipulating.
So you're saying that you would like to see it as the manipulation, to see the manipulation in a visual aspect, kind of like in TL draw. Because if you're referencing to something like utilizing strings, that can't we can't do that. It's only going to be with numbers moving forward.
Okay.
So you weren't referencing to TL draw.
No, I was more so referencing like in output, like,
Right.
you know,
Like,
what are we actually outputting from this manipulation? I'm assuming that's going to be like later. It's a little hard to learn some of this stuff without actually seeing a visual output of what we would be doing, like what the goal of this would be.
oh, got it. Yeah, this is definitely more of an introductory day, kind of like the when we went through, hey, this is Python, and then we learned all of the functions and variables of Python and then JavaScript. We'll get into building stuff starting tomorrow.
Okay.
Erica, I saw your hand up.
No, I was just gonna say, I'm just gonna share a few links then if he wants to visualize some stuff.
Oh, okay, awesome. All right, if there aren't any other questions, we're gonna go ahead and stop the recording here.